Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today is the Independence Day. So I wanted to wish you all a wonderful Independence Day. Today we continue with current electricity. I hope you can hear me. 1 minute. I hope you can all hear me. I hope there is no issue with my presentation. All right. So let me continue with the presentation. So firstly, let's do our business. Today is Independence Day, so we have our Independence Day special. So for students, if you want a 1-year program, 59.95, up until the JEE exam in next August. So you are free. As free people, you can buy the app 59.95 1-year program, right? But you have to buy this week. The other program is 39.95 for 6 months, and but this is a 30% reduction at least from the previous price. In fact, we were thinking of raising prices after this expires. So starting from the 20th or 21st, you will find that this offer is not good. This offer is definitely not going to last after Independence Day. So 1 week, this week is the week, Independence Day week, and you take advantage of it. Use it or lose it, as they say. Okay. So this is your chance. Buy it now. It is there for both Ramanujan and for Sushruta, for both the JEE students and the NEET students. All you have to do is you have to go to look for com.jnanamarga.sushruta or com.jnanamarga.ramanujan in the Google Play Store, and then buy, and then you're all set for a full year, So let's get on with the material. As we were discussing, we will do some problems also today, but we have a lot of material to cover. As you know, there is Kirchhoff's junction law, there is Kirchhoff's loop law, and then you must know how to solve these problems, and you must know how to solve these problems correctly. It is very, very important to know direction, to set the direction, and if you define a convention, stay with whatever convention you are using, but remember the laws and apply them very correctly. You can very easily go wrong with solving problems involving Kirchhoff's laws, but it is very easy if you set up the equation unknowns, and you can cash in with some easy marks. This is requires good algebra, and I'm sure all of you are good in algebra. So you just have to solve and reach an answer, okay, and reach the correct answer. Okay, so the junction rule states that the sum of the currents going into any junction, and the junction is any part of any circuit, is zero. Sum of the currents going in is equal to the sum of the currents going out, which is the same as saying that the currents in a junction is zero, right? The voltage rule tells you go once around any loop. In a solid circuit, you go once around any loop, you will end up with zero voltage. So using a combination of the junction rule and the voltage rule, you set up equations for the unknowns in the circuit, and then you solve for them. Every circuit pretty much can be solved, okay, using Kirchhoff's two laws: junction rule, voltage rule. Once around the loop, V minus IR minus IR1, IR2, etc., or I1 R1, I2 R2, etc., is equals zero, right? Or the currents coming in equals current going out. So look at the junction rule. Let's look at the point A, right? At the junction A, and you always typically focus on these junctions where there are multiple currents coming in, and there you define the junction rule, right? You know the currents that are going out, 3 and 2, and then there is a current 4 coming in, right? So now how do you apply the junction rule? I1 plus 4a equals 3 minus 2a. Notice this minus 2. Okay. So how do you end up with that minus 2? What happens is you say that the current flowing this way is the current is flowing this way. When you solve for it, you however find that it is going that way, right? But you still apply using whatever you started out with. You made an assumption, you stick to your assumption. Okay. So I1 plus 4a equals 3 minus 2a, or I1 plus 4a minus 3a minus of minus 2 equals 0. Okay, so all the currents is 0. So I1 plus 4a minus 3a. So the convention is that everything coming in is positive, right? So that is for A. So now let's do B, right? So 3a, right, coming in is positive. 3a plus 1a plus I2 minus 2 equals 0. That is for B. And so the unknowns are solved using that. Sometimes you will have an equation 2I2 minus 3I3 equals 5. 3I2 minus I3 equals 4. And then you solve for the 2 and then you end up with the result. Okay. So now you here in this case you have the voltage rule, right? So in the voltage rule you have what happens is if you have a current going this way through a resistor, this point has a higher potential than that point. Okay, so this point, let's say the voltage here is V, right? V minus IR equals I2, V2, right? Is the voltage at the output. Delta V is the difference between the voltage that will equal I times R. So the drop in voltage across a resistor, if you're going this way, the current is flowing this way, there is a drop when current flows a certain way, right? So the drop in the voltage is equal to the current times the resistance. Okay, and so if you have a short line and a long line, the short line represents the negative, the long line represents the positive. So when you go this way in this direction, from the short to the long, you say plus. The long to the short, you say minus when it comes to batteries or EMS or voltages. Okay, so in this equation, he is going once around this loop, right? So when he goes once around this loop, he starts from this point, plus 8, minus V1. Okay, then he's going further down through this loop, right? So minus 8, minus 8 again, plus 6, plus 10. Okay, so then he has come once full around the loop. Okay, so that's how you go about it. If you had a resistor, then and the current is when you're going this way, the current is I, then it is I times R1 is the negative. You go minus I times R1 because it's a drop. Okay, so one more time, let's do this problem. Okay, so he is in this equation. If you have typically two loops, you will have two unknowns. Okay, so you make the currents the unknowns. In this case, the let's say you have one current I1 here, another current I2 here. Then this current I3 is I1 minus I2, right? I1 is the current coming in, I2 is the current going out. So I3 has to be I1 minus I2. Okay, so I1 minus I2 equals I3, right? So once you have I3, then you apply the two loop rules and you have two equations and two unknowns. So I'll go once around this loop. Okay, I'm going to start here. Plus 12, okay, minus I3 times 2, which is I1 minus I2 times 2, right? Minus I1 times 2. equals 0. I started at this point, plus 12 minus I3 times 2 minus I1 times 2, and I reach this point again. Okay, so now I'm going to go through this loop. Okay, so I'm going to start here. Okay, minus 6 minus I2 times 2, right? And this way I'm going to say it is plus I3 times 2, and I3 is I1 minus I2. So plus I3 times 2 equals 0. So I've gone once around that loop. Okay, so now I have two equations and two unknowns. I will solve for I1 and I2. The key is writing the loop equations carefully and then setting up the unknowns correctly. Once you've done that, it is just algebra from this point on. Okay, so but then sometimes in addition to doing what is that KCL and KVL as they call it, right? Kirchhoff's current law and Kirchhoff's voltage law. In addition to doing loop law and junction law, you can also use your own cleverness to using what is that to combine resistance. In this case, he finds that 6 and 6 are in parallel, so he replaces the pair with the 3, right? 6 and 6 in parallel is 3, right? So R1, R2 by R1 plus R2 is what? 6 times 6 by 12, right? So that is 3. Okay, so he replaces this by 3. Therefore, now he has a circuit with two equations and two unknowns. Okay? Then he solves for the two equations and the two unknowns. Okay? Now, so this is very, very typical in a lot of questions. Okay, so now sometimes, right, there are two things that you have to learn. Sometimes they will they will give you this infinite number of resistances. Okay, now in the infinite number of resistances case, if you have symmetry, you reuse the symmetry. Okay, this question with respect to the cubic, like a cube of resistances, right? You can see that this and this. Let's say all those resistances are equal, right? This and this is such that the same current probably flows through them, right? And similarly into D, these three will have the same current coming in, right? Now this and this, it's a further I by 2, I by 2. Okay, so the net current going out is 3I, net current coming here is also 3I. So what he is saying is that so how does he end up with 5 by 2, right? Right, so the current supplied by the battery is 6 is so 3I equals 6V by 5R, right? So what is the equivalent resistance between A and B, right? The equivalent resistance between A and B is V divided by REQ, right? And REQ, he tells you, is 5 by 2. Okay. Or REQ, he says V by REQ equals 3I, right? So if I is the current in each of these, right? So V divided by REQ equals 5I, right? Equals 3I. So the current from the battery is 3I. So V divided by REQ equals 3I. So what is REQ, right? So and he is saying that 3I equals 3 times 2 by 5 V by R, right? So how does he end up with that? So I is like 5 by 2 IR equals V, right? How does he end up with that? 5 by 2 IR. So so I plus I plus I, right? So what is the resistance in between this point and this point, right? There is R1, 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 right? So R, and R, right? So there are three R's there, right? So he says that this can be replaced by an equivalent resistance of 5 by 2R. Okay, so and that is if you see, right, the current that if you go once between this point and this point, right, the voltage between this point and this point is V, right? So IR, I by 2R, IR, right? So IR plus I by 2R plus IR equals V. So that's how he ends up with 5 by 2. Okay, so I by 2R equals V, right? Therefore, he uses that to find I equals V by 5 by 2R, or 0.4 V by R. So I equals 0.4 V by R. So now 0.4 V by R, he plugs that in there. Therefore, he ends up with Req equals 5 by 6R. So he is using symmetry to solve this problem. Okay. Now, the key discovery is that the current breaks 3 ways here and then 2 ways here, and it is equal because of symmetry. Okay, and then he uses Kirchhoff's voltage law, right? So if the voltage drop here is I times R, voltage drop here is I by 2 times R, voltage drop here is I times R, and the voltage between this point and this point is V. If you go one loop, right? So he is using Kirchhoff's laws here as well. Okay, so it's a very clever use because he's adding to that the dimension of symmetry. So just like here we did the equivalent resistance and made it, instead of 3 loops, right, we made it just 2 loops. Here he is using symmetry to solve the whole problem using just 1 loop, right? So that was a very clever way, right? So now let's look at this this circuit. In questions, we have to find the potential between points C and D, and in this case he has a capacitor. Okay, so now what happens to a capacitor in the face of a DC current? So let me explain that. Okay, in the face of a DC current, when you first switch on the switch, right, there will be a transitory current going through the capacitor. Okay, which is caused by the displacement current. But then it will then at some point settle down, and at the settle down point there will be no current flowing through the capacitor. After the transitionary period, it will then go to 0. Okay, so the current through the capacitor is going to be 0, and there's going to be, and therefore no current through the resistor as well. So now we have to find the potential between point C and D, potential drop across the plates of the capacitor, right? There will be a potential difference, no doubt. Okay, but there's no current through this, so there's no current through the 6 volts, right? But there is a potential drop between these 2 points. So he's just asking you to solve and then find the potential between A and C, okay, or A prime and C. Okay, so how do you do that? So you have, first let's look at this. Let's say that the current through this is I, right? And the current through this is the current through this is I1. The current going out is I2. So the current through the 4 amps will be let's say the current through this one is I. The current through that one is I2, right? And the current through this one is I. So this the current through this is I1. The current through this one is I2. So this the current through the 4 amps will be let's say the current through this one is I. The current through that one is I2, right? And the current through that one is I2. So but then you can see that this is just a voltage. There's just a voltage across this, right? So the current through this one is this voltage divided by this resistance. Okay. So now this voltage is delta AB. He is he has some value for that. So it is just that voltage divided by 4. Okay. So now okay. So now delta VCD, right, equals delta VCA. Yeah. And so VC minus 2 minus 0.2 times 2 equals VD. Okay. And VC minus VD, therefore he ends up with 2.4 volts. That's the potential drop across the capacitor. Okay. So VC minus 2 minus he has this current as 0.2. Okay. Why is this current 0.2? That is so he has I equals 1.7 amps and I3 equals 1.5 amps. Therefore, the current through this one is 0.2. Okay. So and how does he end up with that? That must be because he knows this value, and we don't know this value from this slide. Okay. But if you knew this value, then you can find the the current through this, and therefore you will know this current, and then you will know this current. Okay. And because you know these two currents, then you know this current. If you know this current, then you can have minus 2 minus I times 2. Okay. And therefore that will be the voltage across AC. Okay. Or CD, or A prime C, or which is the same as A and D have the A prime and D have the same voltage. Okay. So that's how you would find question like that. Okay. So now I have a few simple questions that we will go over. Okay. In a large building, there are 15 bulbs of 40 watts, 5 bulbs of 100 watts, a fan of 80 watts, and one heater of 1 kilowatt. The voltage is 220 volts. Okay. The main fuse of the building will be, okay, so the sum of all the bulbs, right? So in a house, in a large building, there are 15 bulbs, right? So you have 15 currents, right? And 5 bulbs of 100 watts you have, right? Each bulb is I square R, right? So if it's a 40-watt bulb, it's 40 equals I square R, okay? Or V square by R, right? So if 220 volts is the voltage, V square by R equals 40, right? Therefore, R equals, something, right? So you calculate that R, then you calculate the 5 bulbs, V square by R equals 220. V square by R equals 100. There are 5 of those. So you count, you have all these R's, right? So now, what do you do with all the with all these R's, right? So the capacity of the buildings, the building now has to support so many watts, right? So that's the other way to do it, right? So it has to support 15 times 40, 600 plus 500, 1100 plus 400, 1500, 1500 plus 1000, right? So 2500, right? So 2500 is the wattage, and the voltage is 220. So so 2500 equals 220 times I, right? So 2500 divided by 220 is what? The minimum capacity you need. They're not asking you for the maximum, right? So 2500 by 220 is, I assume, I need a calculator for this one. 2500 divided by 220 is probably 12, I think, right? Should be at least 12, or maybe it's 14. So it's a bit somewhere between 12 and 14. Let me get my calculator essentials. Is 11.36. So 12. 12 is the minimum, you know. It has to be a little higher, otherwise the fuse will blow, right? Okay, so now let's look at this circuit. Okay, in this circuit, right, and for this one, I'm going to have to use my pen and paper. In this circuit, the current in the 1 ohm is going to be, okay, so now I'm going to do two currents. Okay, so this is, there are two equations, right? Two loops. Therefore, you have two currents, right? So for the first loop, the left-hand side loop, right? For this loop, right? I'm going to start from this point. Okay. So -6, and I'm going to assume the current in going out this way is I1, and the current going out that way is I2. Going this way is I2. So -6 plus I1 plus or minus I1 plus I2, right? It's coming down, right? So it's flowing this way and it's going out that way. Going down this way and going out that way. Okay. So -6 minus I1 plus I2 minus 3I1 equals 0. Okay. Now let's look at the other loop, right? The other loop is plus 9, right? Plus 9 plus 5 times I2, right? Plus minus I1 plus I2 equals 0. Okay. So now when you simplify these two equations, you end up with 6 equals minus 4I1 minus I2 equals 6. Okay. And the second equation is 9, and 9 equals minus equals I1 minus 4I2. Okay, I1 minus 4I2 equals 9, minus 4I1 minus I2 equals 6. Okay, so now I ended up with two equations and two unknowns. Okay, so now how am I going to solve? Going to solve by multiplying the bottom equation by 4 and then adding the two equations. I multiply the bottom equation by 4, I end up with 4 4s are 16. So the right hand side, I am going to end up with 9 4s are 36 plus 6, 42. Okay, and on the left hand side, I am going to end up with 4 4s are 16 and 17. I2 equals 42. So I2 equals 42 by 17. Okay, and then I1 equals 6 plus I2 divided by minus 4. Okay, 6 plus I2 divided by minus 4. Okay, so now I've solved for I1 and I2, and then the current through the 1 through the 1 ohm is going to be I1 plus I2. Okay, so not very straightforward. Okay, so welcome, happy Independence Day. I was just solving a couple of problems dealing with Kirchhoff's law. Okay, so welcome. So let me continue with this. So I was trying to solve how to solve this problem. Okay, so in this problem, basically there are two equations and two unknowns. So what I was saying is you have one current coming, say this way, right? Coming this way, which is I1, another current coming this way, which is I2. Therefore, the current to this one is I1 plus I2. So if this is going this way the current is also I1, right? So if this current is I1, this current is also I1, and if this this current coming in is I1, this current coming this way is I2, right? Therefore, the current going out through this 3 amperes, 3 ohm is also I2. Okay. Therefore, using this, so now you have two equations and two unknowns. Okay. Now, what you have to do is you have to write the two equations. Minus 6 minus I1 plus I2 times 1 and minus 3 times I1 equals 0. Okay. So, minus 6 minus 1 times I1 plus I2 minus 3 times I1 will equal 0. Now, if I do this loop and let's say I go this loop this way, right? So plus 9, right? Minus 2, and this is if I add this 3 to this 2, minus 5 times I2 minus I1 plus I2 equals 0. So you'll have two equations, two unknowns, and you have to solve for I1 and I2. What is the current through the 1 ohm resistor? It is I1 plus I2. Okay, so you have to set up the equations, you have to solve for I1 and I2, and then you find the answer. Okay, so now, so that was that question. Okay, so you have to do some calculation in some questions. Maybe for some of the NEET questions, it may not be so detailed. Okay, but sometimes you have to solve. You know, sometimes it's not that easy. Okay? A galvanometer, we have not yet dealt with the galvanometer. Okay? A galvanometer is a instrument used to measure current, or which measures current, and you can use it as an ammeter or a voltmeter. Okay? A galvanometer having a coil resistance of 100 ohms gives the full scale deflection when a current of 1 milliampere is passed. Okay? So if 1 milliampere, so it has a resistance, and then there is a reader, right? And so you have the resistance, then you have the reader, right? So now if 1 milliampere is flowing through it, then it will give a full deflection, right? So, but then let's say you want to measure a current which is 10 amperes. Okay, so what do you have to do? You have to connect something in parallel with that. You have to connect what is called a shunt resistor in parallel with that. What is the value of the resistor, right? The value of the resistor has to be such that the effective resistance breaks in such a way so as to so that the current in this one is correctly 1 milliampere when the total current I is 10 amperes. Okay, so for that, you know, you have to connect a resistance in parallel. Okay, so the 100 ohms plus the other resistance 100 times R divided by 100 plus R should then work in such a way that the current through the 100 ohms is 1 milliampere. So the voltage across that is 100 volts, is 0.1 volts, right? So the voltage across that is 0.1 volts. So what is the resistance you have to put in parallel? so that if you have if 1 milliampere is flowing through this, what will be the current through the shunt, right? The current through the shunt will be the remaining from the 10 amperes. So it is 10 amperes minus 1 milliampere. So that is how much? So that is 9.999 amperes. So there is the current through that is 9.999 amperes. The voltage across that is 0.1 volts. So 0.1 volts divided by 9.999 amperes. Okay, so 0.1 volts divided by 9.999 amperes will be approximately this 0.01. Okay, so 0.1 divided by 999 is 0.01, right? So that will give you, so that is the answer. Okay, so how do you convert this galvanometer, which when one milliampere is flowing through it, the maximum, it goes through maximum deflection. So if you want to measure 10 amperes, right, then only a portion of the current will go through the galvanometer. Okay, the bulk of the current is going through the shunt. Okay, but still, you know, whatever portion goes right through this, that will decide the voltage, right? So the maximum voltage it can bear is therefore if 1 milliampere times 100 ohms, that is the maximum voltage can bear. So but then you want the total to be so much more, therefore you need the remaining current to go through that, right? What is the remaining current? If 1 milliampere is going this way by Kirchhoff's current law, the other 9.999 amperes of current has to go through the shunt. The remaining current is going through the shunt. So what is the value of the shunt? The shunt has to bear the same voltage as the galvanometer under 100 ohms, right? So 1 milliampere times 100 ohms is the voltage across that the galvanometer, right? So that is 0.1. So 0.1 divided by 9.999 is the V divided by I is the R. Okay, so that was the way you solved that this question. Now let's look at this question. Okay, in the circuit, right, the current, what is the current in each of the resistances? 1 ohm, 1 ohm, 1 ohm. Okay, so one way to solve this is that you introduce 3 loops, 1 loop, 2 loop, 3 loops. Okay, now that is it can be solved using that 3 loops and 3 current, so then you say this current is I1, this current is I2, this current is I3, and then you look at this current is I1 minus I2, this current is I2 minus I3, right? And this current is same as I3, right? So that is one way to solve this. And then if you solve this, you will get the result, okay? But there is a certain symmetry in this problem, okay? So let's say this voltage and this voltage is the starting point, right? So now, if this is the starting point, this is, and let's say this is V naught. This is also V naught, right? So what is this voltage? V naught plus V naught minus 2, right? This voltage is also V naught minus 2, right? So what is the voltage between this point and this point? 0, because this voltage is V naught minus 2. This voltage is also V naught minus 2. So the current, because these 2 points are the same voltage, there can be no current flowing through this. Only if there's a potential difference can there be a current flowing through this 1 ohm, right? But because this voltage and this voltage is the same, there can be no current flowing through the 1 ohm, right? Similarly, so if this is V naught, this is V naught minus 4, and this is also V naught minus 4. Okay, so the current through this will again be 0. Okay. Then when you look at the third one, right? Again, this is V0 minus 6. This is also V0 minus 6. Therefore, the current through this also will be 0. There will be no current flowing in this whole circuit, which is very surprising, right? But one thing you must note is that normally you would expect to get 3 answers. He is already telling you that this is a little bit tricky, because he's saying the current in each resistance. Okay, so under what circumstance will the current in each resistance be the same, right? So that is the real question there, right? So all the 3 currents are actually 0. Okay, so this is a strict question if you knew how to solve these trick questions, but hopefully they will not ask you so many trick questions. Okay, so so much for this one. Okay, so now I am going to next look at the next set of details that that we are going to try. The next set of details that we are going to try, we are going to learn to understand, will deal with the Wheatstone Bridge. Okay, Wheatstone Bridge. All right. So the next set of ideas, we've already done Kirchhoff's law. I'm not going to revise the material. You already know the junction rule, sigma II equals 0. Then the voltage rule, you go once through any of the loops, you end up with the same answer. So I'll quickly go through this example, okay? Very quickly, very quickly. Let me introduce this. Okay. With this example, how it works is that in this example, you have, let us say that the current in this is I2, and the current in this is I1. This one is I1 minus I2. Okay, so if this one is I1, this one is I2, this one is I1 minus I2, then if you add all these up at this junction, you will end up with 0, right? So I1 minus I2 is the current through this 4 ampere, right? So now I introduce this current as I3. This current is also I3, right? So what is this current? This current is coming in is I2. This current coming in is I3. Therefore, this current is I2 plus I3, right? So now this current is I1. So I2 plus I3 minus I1 is this current. Okay. So now you have 3 different unknowns. So you must write 3 different loop equations. So one loop equation is this one. Okay. So this loop equation, then there is this loop equation, then there's this loop equation. Let's start with this loop equation. Okay. So in this loop equation, I am going to go counterclockwise. Okay. Plus 5 minus I3 times whatever this is, 2, whatever that is. Okay. Resistance. Okay. Maybe it's 2 amps, 2 volts, or there is no resistance here. Okay. Plus 5. This one is minus 2 times I2 plus I3 minus 2 times I2 plus I3 minus I1 equals 0. So that is this equation. The first equation, if you go this way, okay, you go counterclockwise in this loop. So now let's go clockwise in this loop. Okay. So in this loop, plus 10 minus 4 times I2 and minus 2 times I2 plus I3 and minus 1 times I1 equals 0. Okay. So then let's look at this loop. This loop is minus 10, or let me go this way in this loop also. Okay. So plus 10 minus 4 times I1 minus I2 and minus 2 times or plus 2 times I1 plus I2 I2 plus I3 minus I1 minus 1 times I1 equals 0. Okay, so you must always get the convention correct with respect to the loops and how you are going about it. Okay, so you go so that that will take a little practice, and my suggestion is you solve at least 2 or 3 or 4 problems with circuits like this, and you learn to get them correct. You solve the problem from a well-known textbook or from some internet site, and then you learn to get it correct. Once you get it correct, then you have 3 equations and 3 unknowns. Then you can use your standard algebra to solve elimination or Kramer's rule, whatever method you know. Okay, so but that is how you solve these Kirchhoff's laws problems. Okay, so I quickly went through that, and you can solve. This is another problem that he has. I'm not going to go through that, but I'm now going to go through this Wheatstone bridge. Okay, now the Wheatstone bridge relies on this principle that you have 2 resistors like this, and then 2 resistors like this, and there is a ammeter that connects the two. Okay, now there is a circumstance under which the current through that ammeter in the middle will be 0, and that circumstance is when the ratio of the resistors R1 by R2 equals R2 R1 by R3 equals R2 by R4. Okay, so if the resistors are in direct proportion, A1 by A2 equals A3 by A4, then the current through that ammeter or galvanometer will go to 0. And so what they do is, if you have 3 calibrated resistors whose resistance you can then use these 3 known resistors, and they match this ratio, right? You can use these known resistors to match an unknown resistor. Okay, so the problem though is that you need one resistor at least, okay, which can be adjusted. Okay, so one resistor is you can keep changing its resistance, and you know what that value of that resistance is. Then you can find an unknown resistor in order to okay. So look at this. So this is the Wheatstone bridge, right? R1, R2, R3, and Rx. You don't know Rx. R1 is known and it is a fixed value. R2 is known and it is a fixed value and it is very precise. R3 is a variable resistor. What that means is that the value of the resistance can be changed by tweaking a knob to a known value. Okay. Now, in the Wheatstone bridge, when R1 by R3, R1 divided by R3 equals R2 divided by Rx, this will show no current. Okay, so at that point, R1 by R3 equals R2 by Rx. At that point, you will have no current through the galvanometer. So when does that happen? You of course have to apply voltage across the whole circuit. right? And then you have to be able to adjust the resistor R3 to the point when there's no current through that meter in the middle. Okay, so at that point you will have no current, and then the ratio R1 by R3 equals R2 by Rx. Then you will then have no current through the ammeter. Okay, so at that point Rx equals R3 by R1, R2 by R1 times R3. Okay, and R3 is, as you know, variable. Okay, so that is how you the Wheatstone Bridge measures resistance. Okay, now here is a numerical example. Okay, so you have R, right? So this is R prime, right? So now so if you look at this between the points A and B, right? You have a current R going, I1 going here, I2 going here, right? Therefore, there will be a point here when the current in R prime, you could, if you had to adjust it, you could end up with the current through that R prime going to 0 if one of these resistances was also adjusted. Okay, that is the thing with the Wheatstone Bridge. Okay, so I will not further right. So in that situation, so if it was a balanced Wheatstone Bridge, the current through that R prime resistor will be 0. Okay, so under those circumstances, this will happen when the upper one and the lower one, these two have the the equivalent of these two resistors is R plus R is 2R, and 2R plus 2R in parallel is again R. So the equivalent resistor of that is also R. Okay, so so that is the resistance between point C and D. Now we're going to introduce this meter bridge. Okay, now the meter bridge is another form of the Wheatstone Bridge. See, in the Wheatstone Bridge, you have R1 by R3 equals R2 by Rx, right? Similarly, here also it is the same thing. Okay, they introduce a fixed long resistance. Now the ammeter circuit goes and connects to the middle of that of AB somewhere at some point D. Okay, now if you know R and you want to measure S, right? There is what you do is you connect R, you connect S, and then you slide this point D, you slide it to a point where there is no resistance. So when that is the case, you can say that R divided by S is L divided by 100 minus L. Okay, so L divided by 100 minus L, because as you know, SL by A, right? The A is the same, or not when I say S, I mean rho L by A. So when A is the same, the A will get cancelled out, so the rho will also get cancelled out. So you just have L divided by 100 minus L. Okay, so you have that 100 meter. How do you end up with 100? Because it is 1 meter, 100 centimeters. Okay, so you measure the number of centimeters in that bridge that you have moved, and you measure the other. The remaining is 100 minus L, right? So that's why it's called a meter bridge. Its length is 100 centimeters. So L divided by 100 minus L is the other ratio. Okay, so you slide the point D, right? And then till you reach a point where there is no current flowing through that ammeter. And then at that point, you have again reached that Wheatstone Bridge condition, R by S equals L by 100 minus L. And then you will know the corresponding unknown, which is S. Now, a potentiometer is another application of the Wheatstone Bridge. Okay, potentiometer is used to measure the voltage of a cell. Okay, what they do is they connect a cell into the circuit, and then there is a variable resistor, and then they slide that variable resistor. Okay, so now it is also similar to the Wheatstone Bridge. Okay, so there is a potential drop in the wire AB. Okay, so there is a situation in which this galvanometer is connected to 2 points here and here, right? So in this case, right, you have a known E1 and a unknown E2. Okay, so there is a potential drop in the wire AB. The potential drop across AN1 equals PD, and therefore using the two ratios, you can then evaluate E1 divided by E2. Okay, now in the first case, you have I times R equals the E1 is rho times L1 times A, and E2 is rho times L2 by A, right? So so when we say rho L by A, that is merely the resistance. Okay, so so you make sure that the currents are the same through the galvanometer, and then based on that, you can then say that corresponding to E1 there is this current, there is this resistance, and corresponding to E2 there is that resistance. Therefore, using the two, you can then based on the measurement, because the currents are the same, the ratio of the L's will give you the ratio of the corresponding EMFs. Okay, because you have adjusted it so that the current is the same. Okay, so that is the potentiometer. The potentiometer is very commonly used. For instance, it is typically a knob. In a lot of places, it is like a knob which you kind of rotate it, and when you rotate that knob, you adjust the resistance that you're applying, and based on that the EMF, okay, the EMF that is produced. Okay, now there is typically you also you have the you can also use it to find the internal resistance of a battery. Okay, so once you know the open circuit voltage, right? You want to know the gradient that you end up with, right? Because you want to know the internal resistance of the battery itself, and so because of that, the potentiometer is also can be used to find that the internal resistance of the battery. Okay, so I will let that go. The length where the null deflection is obtained is measured, and when that happens, the key is closed and the deflection is measured. I refer you back to the material that is there in your book. Okay, so with that, I'm going to actually end this material. If there is probably a little more that one can do, but I feel that one should move a little bit further on right now, and so starting next class, we will switch gears, because we've spent a significant amount of time in understanding the this material with current electricity. So starting next class, I'm going to switch to magnetostatics. Okay, and so we will start with Lorentz force, and from Lorentz force, we will then switch to Biot-Savart's law and other related material. Okay, so so you have to remember that we will, when we start with current, and Ampere's law, right? So when we start with current and Ampere's law, we have to go back to understanding cross product, and the linkage between electricity and magnetism, which is a tricky subject in itself. Okay, so there are certain conventions. So what I would suggest is, if you do have H.C. Verma, that you read the corresponding chapters there. Otherwise, the other place you can go to is the class 12 NCERT textbook, physics textbook. So you read the chapters there, and then we will get started with this. But it helps to a little bit have read the material, because this material is not so easy, and so I want to take the next step into that. Okay, if needed, I will try to do one or two problems in dealing with this Wheatstone Bridge and potentiometer next time. At the first 5-10 minutes, I will try to plan for a maybe one or two problems there, just like we did one or two problems with Kirchhoff's laws today. So we'll do one or two problems, and then we'll move on, because we have a lot of material to cover with magnetostatics, and then we have to go to electromagnetic induction, then we have to go to AC circuits, etc. Right? So next class we will do magnetostatics. So till then, try to get yourself ready for the material, and we will take it from there.